Okay, so this is the marking period 1 review packet. So let's make sure you have your reference tables out as well as a calculator, and highly recommend a scrap sheet of paper so you could be doing calculations for the ones that require it. All right, the diagram below shows a section of a 100 milliliter grad cylinder. When the meniscus is read to the correct number of sig figs, the volume would be. Okay, so the first thing you need to do is take a look at the scale. So it looks like here's 70 and here's 80. So each of these go up by 1 whole milliliter, which means you can estimate one place beyond that, which would be the 10th place. So only one beyond what is written here. So 70, 71, 2, 3, 4, 5, 6. So between 75 and 76. So we're down to A and B. And it looks like it's right a little bit over half. So I'm going to go with 75.7. And again, the reason why it's not 0.70 is this is too many sig figs. You would need to have the scale go to the tenths in order to estimate to the hundredths, and we do not have that. Number 2, which set of lab equipment would most likely be used with a crucible? So a crucible is a teeny tiny little thing. It looks like an acorn. It's not very good. And so you would need a clay triangle. So these do not have clay triangle. And crucible tongs, which is choice A. So 2 A's. Number 3, which temperature change indicates an increase in the average kinetic energy of molecules in a sample? So average kinetic energy is code for temperature. So the first thing we need to do is make sure all the temperatures are in the same scale. So right now they're not. We can't compare them. So let's go to the reference table. And on table T, we're getting there. So table T shows the formula to convert between Kelvin and Celsius. So any value in Kelvin, to get values in Kelvin, you would just add 273 to anything Celsius and subtract otherwise. So coming back here, first thing we need to do is make everything into one scale. So how about I make everything Kelvin? It doesn't matter what scale you choose. I'm just going to make everything Kelvin. So 15 plus 273 is 288. So which temperature? We're looking for an increase in temperature, and I already know that's an increase from 288 to 298. So that's my answer. I guess just for the sake of example, I'll do the rest. So this is 310. 310 goes down. This would be 273, so that's going down. And 25 plus 273 is 298. So that's going down. So yes. How many decimal places should be in the answer if 2.214 is added to 6.3? So 2.214 plus 6.3. The rule of sig figs when you add or subtract is the fewest number of decimal places. So this number has 3 decimal places, not total sig figs. Total sig figs would be 4. 1, 2, 3, 4. But 3 decimal places, this only has 1. So 1 decimal place. When 1.255 grams of X reacts completely with 3.2 grams of Y, Z is the only product of the reaction. What is the total mass of Z expressed to the total proper number of sig figs? So we are adding these. So 1.255 plus 3.2. So 1.25, I'm going to use my calculator because, you know. So my calculator gives me 4.455. And so you would be, it would be easy to just choose that. However, just because the calculator gives that to you doesn't mean it's the right number of sig figs. So this has 3 decimal places. This has 1 when you add or subtract. So we want 1 decimal place. So 4.45, this 5 would round that up to that. Choice C. Which measurement contains 3 sig figs? So again, here's, oh my gosh, America, not good. So if decimal place is present, we're going to go from left to right. And as soon as we count something that's not 0, we're going to count sig figs. So in part A, this is 1 sig fig. In part B, this is 2 sig figs. In part C, this is 2 sig figs. In part D, this is 3 sig figs. So number 6 is D. Number 7, 1 kilojoule is the same as. So back on the reference table, right on the front, sorry to make your head spin here, it shows the metric prefixes. So kilo is 10 to the third, which means 1,000, which means 1 kilo anything I don't know, kilogram, it's going to be equal to 1,000 little grams. 1 kilometer is equal to 1,000 meters. So kilo means 1,000 times larger. So you'd have 1,000 little pieces within there. So over here, 1 kilojoule is equal to 1,000 joules. Number 8, we were just talking about the temperature conversions. So this is degrees Celsius plus 273. So 56 plus 273 gives me 329 Kelvin, not negative. And remember, it is not degrees Kelvin. A cube has a volume of 8 cubic centimeters and a mass of 21.6. The density is what? So on the reference table, table T, again, here we go, all the way down. You will find the formula for density. You do not need to memorize it. The formula for density is mass divided by volume. I highly recommend putting D over 1. That way you have 2 equivalent fractions and you can cross multiply. So you don't really have to cross multiply here because we're just looking for density. So 21.6 is our mass, 8.0 is our volume. So I'm going to put that into my calculator and I get 2.7. So now the question is, which one of those is the right answer because of sig figs? So this one has 3, this one has 2, and so your final answer should have 2 sig figs, choice A. The following weighings were made during a laboratory exercise. So the evaporating dish alone has 59.260 grams, and then the sugar sample is 1.61 grams. What is the total mass? So we're going to add that together. So on my calculator, I'm adding those numbers, and I get 60.87 according to the calculator. But is that the proper number of sig figs? So again, we are adding. So this is 3 decimal places. This is 2. So I want 2 decimal places. So as is, B. I'm not going to add a 0 for number 10. Number 11. In experiment, the gram atomic mass of magnesium was determined to be 24.7 compared to the accepted value of 24.3. What is the percent error? So back to the reference table. The percent error formula is found here. Measured minus accepted over accepted times 100. There are no negative values. So if you subtract your numerator and it becomes negative, just make it positive. Just remove a negative sign. So I'm going to say 24.7 minus 24.3 is going to be 0.4, and that's going to be divided by your accepted, which is 24.3 times 100. So let me do that. And I get 1.646, which is 1.65%. We're going to have another percent error here. So now this is a little bit different because we're looking for the difference here. So who has a percent error of 5? So we just have to do this. So these are all measured values. And we're just going to plug it into the formula. So 36 minus 31 is 5 over 36 times 100. Which is 13.8, so it's not A. In B, it would be 0 over 36. That's 0% error. Nope. 37.8 minus 36 is 1.8 over 36. 1.8 times 100 gives me 5%. That's my answer. 41. I'm not even going to do the last one. It's just not. Okay, so 13. How many grams of water will absorb a total of 2,520 joules of energy when the temperature of the water changes from 10 to 30 degrees Celsius? So back to the reference table, table T. Here we are at Q equals MC delta T, where Q is heat, M is mass, specific heat capacity is C, and delta T is the change in temperature, which is defined as T final minus T initial. The specific heat capacity, if you're dealing with water, hold on to your hats, going to the front of the reference table. If you're dealing with water, is found here, 4.18 joules per grams Kelvin as written on the reference table, or grams degrees Celsius. So let's go back to the question. Q equals MC delta T is our formula. We are looking for grams of water, so 2520 equals our M, or our X, if you want to call it that, 4.18. And then T final minus T initial gives me a difference of 20.0. So this is 20.0. So let's do some algebra. 4.18 times 20 gives me 83.6 times M equals 2520. I'm sorry, this is messy. Divide both sides by 83.6, so 2520 divided by 83.6 gives me 30.14. And so I'm going to go with whatever's closest, which is choice C, 30.0. Here we go again, which is the total number of joules. So we're looking for Q. Q equals mass 15, specific heat of water 4.18. Now, if in the question you're not talking about water, you're talking about like iron or something, that would have to be provided to you in the question. T final minus T initial would be 10. So 15 times 4.18 times 10 gives me 627. That's not a choice. However, if we round to 2 sig figs, which 15 is 2 sig figs, we're going to go to 630. Which sample is a homogeneous mixture? So the only one that is not a pure substance would be something that has two things here, aqueous. That means sodium chloride solid and H2O liquid. We are dissolving in water, so that's why it's a mixture. The reason why it's homogeneous is because all the particles are evenly distributed and uniform throughout. All right, number 16 is a tricky one. When sample X is passed through a filter paper, a white residue Y remains on the paper, and a clear liquid Z passes through. When clear liquid Z is vaporized, another white residue remains. Sample X is best classified as heterogeneous mixture, homogeneous mixture, element, or compound. So I'm going to say that it is definitely not an element or compound because we are able to separate it by physical means. So if you're separating something by physical means, it's a mixture, whether it's heterogeneous or homogeneous. Well, the reason why it is not homogeneous and it is heterogeneous is the fact that we have residue remaining on the paper. If it was homogeneous, it would be totally uniform and it would all go through, but the fact that we have something on the filter paper makes it heterogeneous. 17, a mixture of crystals of salt and sugar is added to water and stirred until all solids have dissolved. What happens? So I know that salt will dissolve in water, homogeneous. I know that sugar will dissolve in water, homogeneous, which means it's not going to be C or D. But I do know that it is, because homogeneous, you cannot filter it. The particles would be so small and homogeneous, it would go all the way through, pass through a filter paper. So to separate that back out, you would have to boil or evaporate. What is an identifying characteristic of a mixture? A mixture can consist of a single element. No, that would be an element. A mixture can be separated by physical means. Yes, that's just what we talked about. A mixture must have definite no and no. At room temperature, sand and water can be separated by. Well, I know, first of all, I'm just looking. Maybe I'm confused at what ionization means, so I'm going to skip that for right now. I know that filtration is not going to work because I know that sand is too big to go through a filter paper, so it can't be that one. Oh, wait. Shoot, that's exactly what the answer is. I know that because the idea is we can separate it. Yes, so if you pour sand and water through the filter paper, the sand will stay in the paper and the water will go through. I'm sorry, that it was choice C. Combustion, this is a reaction where hydrocarbons react with oxygen to produce CO2 and H2O. That's a chemical reaction. Sublimation is when a solid goes straight to the gas phase. There's a phase change. And ionization is when elements are either gaining or losing electrons. So filtration is the answer. Which mixture can be separated by using the equipment below? So again, I'm going to look for the solid. This is sand, SiO2. And the solid is not going to be able to pass through the filter paper because it is solid. Everything else is aqueous, which means dissolved in water, and those all can go through. So 20 is A. 21. Two substances in a mixture differ by density and particle size. These properties can be used to separate, chemically combine, determine the freezing point, or predict. No, the fact that they differ in density and particle size helps us to separate them. So that is the answer. If a student pours a mixture of sand and salt water through I feel like we've had this before. What will be found in the beaker after filtering? So the salt and the sand are all dissolved. Well, sand won't dissolve. So sand will be in the filter paper, and what will be in the beaker? The salt will, but also the water that dissolved it. So there we go. Mixture of sand and table salt can be separated by filtration because one is dissolved in water and one is not. I'll admit, this is a lot of repetition. A chemical change. Number 24, a chemical change will create something brand new. So a nail rusting, water boiling, chopping wood, or cutting paper. So C and D are just changing size. B is changing our phase. So water boiling is H2O liquid going to H2O gas. So it is not that. Nail rusting is forming a brand new substance. So that is it. Which does not involve a chemical change. Burning of gasoline, dissolving a sugar cube, the rusting of a car, the digestion of food. So it has to be the dissolving, because dissolving is not a chemical change. It would just be particles becoming homogeneously distributed throughout the water. We could recover that sugar through evaporation or boiling, but we could not regain gasoline once we burned it. We could not regain the metal of a car after it's rusted, and we can certainly not regain food after it's been digested. Those are undergoing chemical changes. All right. A can was filled with crushed ice, sealed and masked. The ice was melted slowly by warming the can. No water vapor escaped, no air entered. If the can is masked again, so what's going to happen? So basically we had ice, it melted, and it was in a closed container. And this is showing us the law of conservation of mass, saying that mass would not be created or destroyed. Now, if you had opened it, if you had let it be open, then we would be losing mass only because the gas would have escaped. However, since it's a closed container, nothing's entering, nothing's leaving, it would have to be the same. Come on, lab safety, which is not a safe lab procedure. Not safe. Wearing goggles? No, that is safe. Wafting is safe. Pouring chemicals down the drain. You don't know what can go down the drain. Sometimes it's not good. The ratio of an object's mass to its volume. I feel like we've seen this before. Density. Number 29, consider the liquids. If you pour all 4 liquids into a glass cylinder, the densest liquid will settle to the bottom and the least will settle be at the top. Okay, wow, they even tell you that most dense will be at the bottom. So it looks like we need to calculate density for those. So mass divided by volume, we have 3 divided by 5. So this first one is 0.6. 6 divided by 20 is 0.3. 5 divided by 15 is 0.3 repeating. And 4 divided by 10 is 0.4. So the most dense is liquid 1. So can't be those. And then 0.4 is liquid 4. So 1 is at the bottom, then 4. So there we go. All right. Which graph shows the most probable effect of environmental pollution on the chances of human survival? So in all of these, as pollution increases, that's our X, what's going to happen to human survival? I'm guessing, you know this, maybe you don't, pollution would decrease our chance of survival. So it would be B. So this is just a silly read a graph. Hopefully you can get that one right. Which form of energy is transferred when an ice cube at 0 degrees Celsius is placed in a beaker of water at 50 degrees Celsius? So it looks like we have a difference in temperature. And I know that the ice will melt. So we're talking about heat energy, which is thermal. Chemical and nuclear, definitely not. Electrical energy, there's no form of electrical energy going on here. There's no plugging it in. There's no metals in an electrolyte, anocathode, any of that. We haven't even talked about that, so it can't be that one. In number 32, we're talking about heat flow. So heat flows from area of high temperature to low temperature. It's a theme in science as we're going from high to low. Sometimes it's concentration, sometimes it's temperature. So whoever's hotter is going to give off its heat to lower. So the cube of iron is at 20, the copper is at 60, so we're going to flow from the copper to the iron, which is choice A. 33, 3 forms of energy. Electronegativity is not a form of energy. Temperature is not either. That's average kinetic energy, so it would have to be B. That's just definitions. We had those in our notes. Another average kinetic energy. So let's make them all talk the same language. So I'm going to make everybody talk Kelvin. So 27 plus 273, this is 300. 12 plus 273 is 285. So who is talking at the highest average kinetic energy? That would be choice C. Again, this is not great. Average kinetic energy. 50 kilojoules to joule. So let's do some dimensional analysis. I'm going to do it here to the left. So 50 kilojoules is our given. I know that I seek joules. I know kilojoules. In 1 kilojoule, I have 1,000 joules. So 50 times 1,000 gives me 50,000. Uh-oh, that's not a choice. So I need to put it in scientific notation. Scientific notation, you need to have a 5, 1 digit in the ones place, times 10 to the 1, 2, 3, 4. 5 to, it's not a question. It is indeed D. Okay, so I'm going to actually erase this now. I need more space. So this is Q equals MC delta T. However, we are looking for the final temperature. So we're going to actually have to substitute in the definition for temperature change. T final minus T initial. So 100 gram sample, so 100. It's water, so 4.18. Absorbs 8360. And T final, I don't know. T initial is 22. All right, so I know that's a little messy. So 100 times 4.18 gives me 418 times the quantity TF minus 22. So let's divide both sides by 418. So 8360 divided by 418 gives me 20 equals TF minus 22.0. So we need to add 22.0 to both sides. And so I'm going to get 42. Number 37 is D. Yes. 0 Kelvin on the Celsius scale. So 0 equals X plus 273. So let's subtract 273 from both sides. Get that one. Oh gosh, this again. A mixture of sand and water at room temperature. So sand and water, you'll see the differences. It would be heterogeneous. The components are in the same phase or different phases. No, they would be different phases because the sand is still a solid. It does not dissolve in water. Water is liquid. A component of the mixture, each component gains new. So again, let's think about water and sand. Each component gains new properties. No. They lose their properties. No. The proportions can or cannot vary. Yes, they can vary. Because maybe sand and water isn't the best example, but salt water. So salt water from the ocean is very, very salty, lots of salt. The salt water in your contact solution, saline, not a lot of salt. So it would be different components. A mixture of 3 substances. Okay, so we have particle diagrams. The white circle is one element, black circle is a different one. So let's talk. So in box A, we have a white-black combo, and then we have 2 white. So that's only 2. In B, we have the 2 whites, and then we have the 2 blacks, and then we have white-black. So that's got to be our answer. 41 is B, yes. 42, powdered sulfur is yellow, powdered iron is gray. Thanks for letting me know. When powdered sulfur and powdered iron are mixed, what's going to happen? Now, I'm not asking you to specifically know. I just want you to know that when we have a mixture, we remain our properties. Our properties remain. And I know that iron is magnetic, so that's going to stay. It's going to be maintaining its properties. Table sugar can be separated from a mixture of sugar and sand by adding, we wouldn't be adding more sand. We'd add water, which would dissolve the sugar. We would stir it, of course, to help it dissolve, and then we would filter it because then the sugar water would come out and the sand would stay in the filter. Distillation is the process by separating 2 liquids by different boiling points. So we're not dealing with liquids. We're just, and there's 44. It has to do with boiling points. So like alcohol and water have different boiling points. One will boil off first, cool, condense, and then be separated out. And G, here it is again. Okay, so what is going on here? So we have a drop of food coloring and water, and then after a while, it looks like we have separating out of the colors. So that is what we call chromatography. The root here, chroma, means colors. We've just spent 2 questions talking about what distillation is. That's the separation of liquids based on boiling point. Titration is a process by which acids and bases come together to neutralize. That's not this. And electrolysis has to do with, a battery or something, so that's not it. Chromatography. Which type of change must occur to form a compound? So we're forming a compound. So it's not going to be a phase change. It would be a chemical change. Nuclear change? No. Physical change? No. So 47 should be A. 48, the diagram shows a chemical equation with the substances on one side hidden from view. From what the law of conservation, what would be true? So here we have reactants and products. So the law of conservation of mass says mass or matter cannot be created or destroyed in a chemical reaction. So the products must weigh more than reactants? No. Energy is neither absorbed nor released? No, because we're talking about mass. Substances on either side must be the same? Well, no, because it's a chemical reaction. You'll have different things, but the number of atoms must be the same. So, again, a chemical reaction makes bonds, breaks bonds, shifts things around, but the number of atoms must be the same. Number, but the arrangement is different. Which statement concerning elements is true? Different elements must have different numbers of isotopes, different number of neutrons, mass, protons. Yeah, it's D. Because the same number of protons, this is called atomic number. This is how we organize the periodic table. Because carbon cannot be decomposed by simple chemical methods into 2 or more different substances, it is classified as a mixture. Holy cow, an element. I looked at mixture and I said it. But no, carbon is simply an element. It's on the periodic table. Look for it there. A compound would have 2 or more elements chemically combined. So in part C, we have a carbon and we have an oxygen. This is one element. This is called a diatomic element, and this is tricky. That is wrong because that is cobalt. Again, I feel like we had this already. So what's going to go through the filter paper would be water and the salt, because the sand stays in the filter paper. Yeah. Sorry. Which of these explains why the pebbles are below the sand? So pebbles are more dense than sand. Temperature of the water is high enough to melt. No way. Sand particles dissolve more in water than pebble. No, you'd have no beach. Sand particles trapped enough air to make them float. No. Density. That's what happens. Settles it out. 53A. What is the length of only section A? So section A looks like it starts around 7, ends around 11.5. 11.5 minus 7 would be 4.5 centimeters. And so 23 millimeters would be 2.3 centimeters. Yeah, so let's just see. Okay, so 4 solid objects made of the same uniform material. Volumes of the sphere and the bar are not given. What will occur when the sphere is heated and expands? So the mass will not change. However, when you heat things, their volume should increase because particles are moving faster. So it should be choice C. Why is it easier for a person to float in a salt water of the ocean than fresh? Salt water is dense, less dense, more bubble. No. Salt water is more dense because it's got more stuff in it. And so that's why a person will float. So anything that is less dense will float. God, this is the same question. This is not great, guys. Say what is not safe? Actually, it's not the same question, but it's B. It's the same idea. Why is it advisable to use tongs? It's hot. Goodness. Some household chemicals should not be combined because combinations, chemical reaction. Produces nuclear waste? No, nuclear waste is not chemical waste. Is against the law. What the heck? Yikes. Heat flow, hot to cold. A to B is from hot to cold, so that's probably our answer. Let's just make sure. A to C, no. B to D, no. D to C, no. So hot to cold, A, 60s A. All right, which group of atomic models is listed in historical order from the earliest to the most recent? So we start with Democritus or John Dalton, which said atoms are hard, indivisible spheres. Then we go to J.J. Thomson, who said plum pudding model. That's not a choice. Then we went to Ernest Rutherford, which was the gold foil experiment, which had the nucleus. I guess that's not there. Then we have the Bohr model, which is electron shells. And then we have the modern model, which is orbitals. So B. Which explains or describes the charge of mass of a neutron. So if we go to the reference table, a neutron, whoops, here. This is the mass, this is the number of protons, and then there's our symbol. So the mass is in the top left. So mass of a neutron is 1. So coming back here, approximate mass of 1 AMU. So neutrons have no charge, neutral, so no charge, mass of 1. Which subatomic particles were discovered as a result of the cathode ray tube? That would be the electrons, J.J. Thomson. The overall charge of a nucleus in a fluorine atom. So remember, the nucleus has protons and neutrons. And so neutrons have no charge. So we don't care how many neutrons there are. So basically, we need to see how many protons there are in fluorine, and that will be our answer. And I'm going to apologize in advance because the periodic table is sideways. So here's fluorine. Fluorine has 9 protons. Protons are positive, which means plus 9. Which particles have a mass of approximately 1 atomic mass unit, or AMU? I've already talked about that neutrons do. Electrons have a mass of 1 over 1836 of an AMU, or essentially 0, so definitely not those. So then we're down to proton and positron. So let's actually go back to the reference table. Proton versus positron. Proton has a mass of 1. I see that here. Positron has a mass of 0. So a neutron and a proton. The nucleus of any atom would not be negative. Does not have any electrons. Yeah, it's an overall positive. So the nucleus is positive. We have protons and neutrons, and electrons are way out here, and they are negative, and that's why we have a canceling out of charge. The protons, which are positive, and the electrons, which are negative, cancel out. Results of the gold foil experiment. The conclusion is an atom is mostly empty space and has a small, positively charged nucleus. Because remember, most of the why did I draw that? Most of the gray. Most of the beam went straight through. Some got weird and very, very few came back. That is a terrible diagram. I apologize. But that just shows that the very, very small positively charged nucleus hit those positively charged alpha particles, and they had to repel. All atoms of the element vanadium must have... So what is the same with all elements? They must have the same number of protons. That's not a choice here, but atomic number is. Atomic number is the same as number of protons. All right, so in your electron shells, as you go further and further away, energy is increasing. So compared to an electron in the second shell, the first shell is lower, yes, because third shell will be higher. They would not be the same. An atom of chlorine in the excited state. So let's go to periodic table and find chlorine. And chlorine has an electron configuration of 287. And you would be, you would be tempted to just say 287. but this is what we call the ground state. So we want the same number of electrons just shifted upwards. So we still need to have 17 electrons total. We just need to be shifting upwards. So in part A, we have more electrons. That's not correct. In part C, we also have more electrons. But in part D, we had 1 electron from the second shell jump to the third shell. So that is why that is our answer. It's still 17 electrons. They're just shifted. Which atom in the ground state has a partially filled second electron shell? Hydrogen, lithium, potassium, or sodium. So let's go to periodic table. Hydrogen just has 1. Lithium says 2-1. Sodium has 2-8-1. Potassium 2-8-8-1. So partially filled second electron shell. That would be lithium, because it's 2-1, and that's it. So everybody else fills this up to 8, or with hydrogen, it doesn't even have that. So lithium, it says 2-1, so this is not completely filled. Which statement describes 2 different isotopes of carbon? So isotopes of carbon would have the same number of protons, which is the same as atomic number. So same atomic number. However, they have different masses, which come from different numbers of neutrons. So the same number of neutrons, no, same number of neutrons, no, different number of neutrons, same atomic number, yeah, see. Isotopes of the same element. So again, we'd have to have the same number on the bottom, because this is protons down here, mass is here, symbol here. So A works. A is the only one that works. Because they're both nitrogen with 7, but notice how we have different masses. This one over here has more neutrons, just adding extra weight. All right, average atomic mass. This formula is unfortunately not on the reference table, but all you're going to do is multiply these together and add them to these multiplied together. But percentages are multiplied by 100, so we just need to take those out. We divide by 100. So 60.11 divided by 100 is 0.6011. Multiplied by 68926, added to 0.3989 times 70.925. So that would be A. Yeah. Finally, diagram 1 shows an atom of hydrogen showing the nucleus and the electron from the first shell. What's going on in diagram 2? So it looks like that 1 electron jumped from the first shell to the third shell, which means it is called an excited state. A positive ion of hydrogen means you lose electrons. A negative ion of hydrogen means you gain electrons. We didn't lose or gain. We still have that 1. It just shifted upward. The ground state is what we consider the normal state, and hydrogen's normal state for electrons is 1 in the first shell. So since it went up to the third, it would be considered an excited state. So I hope this was helpful. If you still have questions, please ask. Please come see me. All right, thank you. Bye.